Hi, Mark Knutson here for the fifth and final time on this video series looking at baseband link control of Matlab from Matlab Cockpit, completely remotely controlling SystemVue through a tool called Bench Baseband Link. So thanks for your time and attendance if you've been able to go through the first 4 videos in this series. And we're going to do one final video here and do one last look at a case to kind of really shake things up. And it's good to kind of go back and look at what we've done, just kind of so give you your history of I Survived, the best baseband link video series in SystemVue. Hopefully learned a lot. And let's do a quick summary of what we learned. So in the first example, we basically went through what it takes to run the shipping example. And so we looked at, changing the run from Matlab from 0 to 1, and that would certain parts have been set up to run from equation, and they would be turned off when run from Matlab's 1, but the ones that Matlab would see when it's controlling SystemVue would be active. And so in this case, we would have one source and one sink, and then our RF channel that's using data flow parts. And we showed how to plot the voltage spectrum at the input and the voltage spectrum at the output. And that was the first one. We showed what it takes if you have an RF link, that there is a behavioral model cache, because it's a frequency domain model, and SystemVue needs to convert that into the time domain for use in data flow. And that's where baseband link resides. And we showed that if you change one of the cardinal parameters like F carrier, sample rate, in this case, we changed the carrier frequency from 100 megahertz to 220 megahertz, that we needed to clear the behavioral cache, rerun the simulation, save it, and then when we had a corresponding F carrier change, parameter change in our Matlab code that matched what we had in the cache, it would run as expected and not flag an error there and give us our 220 megahertz. And again, you only have to do that when you're dealing with RF link. So that was the first example. And the first example, we also added the ability to first time look at looking at the ADX file that's generated anytime you run a SystemVue simulation, and basically post-process and grab sync data that results from that SystemVue simulation, which is very useful. We'll see it in the later videos with a beamformer, that we can quickly get a beamforming plot that way, and data from our directivity, theta, and phi grid if we wanted that, as one example. So that's the first example. Hopefully you found that useful. And we definitely also looked at tips like what you need to have to run the simulation in Matlab. And you need to basically put C program files, Keysight, your SystemVue installation directory / baseband link in your Matlab path, and you should be good to go. Then the second video series, we looked at troubleshooting. If you encounter any errors, kind of the most common errors, and those that we focused on, they all get flagged with this SystemVue MEX error analysis error. And then the first one had to do with something failed to run. That usually means on the analysis side, on the SystemVue side. So it encouraged you, and we looked at how to use the systemvue.config.getErrorLog to see what the error is, and it gives you some breadcrumbs to where it's failing, and you can figure it out. In our case, we had a problem where the cache in the RF link wasn't ever proper, and so it said it needed to be regenerated. But this error can point you to other issues with the simulation on the SystemVue data flow end, and help you figure that out. The second error that we looked at had to do with the TCP server being forcibly closed, or just connection failed. And that is the communication mechanism by which Matlab communicates with something called SystemVue Engine, which is a kind of a blind background version of SystemVue process running. So it can even run on Linux, and Matlab on Linux. And basically, if that breaks down, you're not communicating with SystemVue. So we went through how to fix that. And the third error is a deadlock error, or a synchronization error, but it depends on if you have different baseband link sources, multiple or single, and multiple single baseband link syncs, and if they're at different data rates. On today's video, we're going to look more closely at that, but you can get into deadlock errors, and if you go to that part of the documentation has some good tips on scheduling and polling and advanced functions if you need to, wait till the data is ready to set or get, and how to control that. The third video and the first beamforming example that we did had to do with basically generating a baseband link modulated source from Matlab. So we use a baseband link part in SystemVue, and the modulation was generated in Matlab and passed in at this point, at this source, baseband link source. We went through our data flow design. In this case, it was a beamformer, so synthesize the beam weights, splitting into an 8x8 array, beamformer array, and then we did phase shifting and fed in the weights for the tapering and generated the beam. This was an antenna array TX and generated the far field beam. And then we actually captured the voltage spectra at that point of the far field beam at number 5 location. So we generated the beam and then captured in SystemVue syncs, not baseband syncs, the antenna directivity, the theta and the phi grid, so we could do the antenna pattern. So in this case, this first beamformer example, the modulated source was controlled by a baseband link source from Matlab, and then the far field spectrum, voltage spectrum, we captured with a baseband link sync. And then we had some SystemVue syncs that we captured other data and used the ADX file to capture that and plot that, all in Matlab. The second beamformer example that we looked at, instead of using, it was all syncs. It had 3 syncs, baseband link syncs. There was no baseband link source. We used an internal 16 QAM source in SystemVue at location 10 here as our source. We did not use the baseband link source, and we went through our data flow. The same data flow design does the beamforming, and we did not capture the spectrum at this location. Instead, we captured the antenna pattern live, I should say, from in MATLAB directly from the simulation, and we had to unpack it because it's a matrix data, 361 by 181, I believe, matrix, and we had to package that into array vectors because that's how baseband link needs to hand it over to MATLAB right now. So we use the unpack data flow part to do that, and so we had 3 different syncs. If you looked at the code in the second beamformer example, it was very simple, just 3 get data calls in the Matlab code tied to those syncs, and then that was all it was. If you compare that against the first example, where we had an actual Matlab baseband source and sync, it was an actual like for loop, right? Where we had a precise number of blocks, where we used the set data command in a loop to set the 16 QAM signal, start index to stop, and then we captured it. In the third example that we're going to look at today, it is very similar, but let's show you how it's different. So if we go, and I've got it loaded up here, example 3, beamformer example. If we put this in what MATLAB sees, run from MATLAB, as we've done in the previous videos, we see that we're sending in a 16 modulated signal here for the baseband link source. We go through our beamformer like before. Now we got rid of that our antenna array TX and that far field beam, so that was kind of at a constant data rate. We got rid of that whole path, and all we're doing is sending. There's only a baseband link source, nothing else, and then we have SystemVue syncs to capture the data coming out of this beamformer, the rendered beam. So the difference is we got rid of that far field path that had a baseband link sync, and so we're sending in, remember we're passing in the sample rate from MATLAB, 48 megahertz, passing that in to the baseband link source, and you see that here, base sample rate passed in from MATLAB, and then it's coming in, going through the data flow, and it does get downsampled here, and then it goes into our beamformer, and we capture the data. So let's take a look at the MATLAB code to get that and see how that works. So let's see, make sure I'm in the right one. All right, so you see, let me clean this up. So if I run this at beam theta 30, runs pretty fast. And we've seen this code before. We generate the modulated signal. 29x is the kind of the final modulated waveform. And we open the workspace, example 3 workspace. We set the parameters with the tied to the analysis data flow DF1 analysis in SystemVue, and we set all the parameters. And then in this case, we have one baseband link source from MATLAB, and that's this guy right here. And in this case, we start the simulation, and we're just looping around 100 samples, and we set data because we only have a baseband link source. We set the data, put it into, and stop the simulation, get the ADX file that results, the encrypted dataset file, plot our antenna pattern as we've done before. Everything's pretty makes sense as we've seen before. The directivity is what we expect for 30 degrees theta, minus 30, minus 19, minus 13. And we'll see that. And so pretty cut and dry. But what makes this different is we got rid of that plane and that previous path where we went and grabbed the far field voltage spectra. We got rid of that, and we're just capturing it here in a SystemVue sync. So let's go to the document. So the document shows how to set all that up, and then it basically goes through the code like I just did really quick. Let me get down to the section where we have the 100. So then in the document, we ask, what happens if you change this to something else, not 100? Why is it 100 in the script? So if we change this to 2000 and we run this, it errors out and says basically set data failed because it hasn't been started or stopped. There's some synchronization problem. If we didn't know this was supposed to be 100, how would we figure it out? And in SystemVue, there is a the data flow controller. If you go to the options tab, it has something called display data flow information. So if you check that, run the simulation, it'll generate a table of the data flow rates, right? And if you follow this through, it's like data flow kind of consistent 1, 1, 1, and then you get to 100, and that's at the downsampler CX reduced data. So we can remember I said we downsample by 100 because we didn't need all of that data to render the beam. So we're actually the data rates change by a factor of 100. This could be a mixer. There's a filter. There's many different ways in data flow to change the sample rate. So we actually go from 48 megahertz, which is set here, and then we downsample it by 100, and is what's getting set here. So the document example goes through setting up what I just showed you, the data display information, figuring out where the difference is in the data rate change, and then shows how the sample rate is set. And if you go back to the 100, it runs, no problem, as we did before. And so the rest of the example is kind of what we've seen before. but just wanted to point that out as a good example to play with in understanding a synchronization problem or a deadlocking problem. And this is the 30-degree case, so you're going to see what we saw before in SystemVue, and you get this is at 30. This is what the beam looks like in SystemVue. Get the 30, and the directivity is the same, minus 30 and minus 19. Now if we change this to 45, rerun our simulation, you'll get the let me load that again. I think I did something wrong. If you run that at 30, you get that. If I change this to 45, you'll get a different beam. I gotta delete that. So I change this to 45, rerun this. Now we get the 45 as expected. And the directivity is gonna change, and we can see that here. So we go back up here and change this to 45. And you'll should see the directivity change as well, and it does. So I hope you found this useful, this video series. Wanted to give you some of the basics, the key points, things like that you want to pass in parameters and equations at the schematic level. That's very important. And then digging deeper when you have different numbers of sources and sinks, whether they're baseband link sources and sinks, and at different data rates or multiple versions of them, and it can affect the code in the different examples, right? Like in the first example, we used this code, kind of a block code and a for loop. In the second example, it was just some get data commands because it was 3 different sinks. And then this third example, we actually had different data rates, so we had to use we had you have a precise number of 100, was the data rate that we needed to pass in and keep that uniform to process it correctly in Matlab. So hope you found this very useful, along with some troubleshooting techniques. And if you have any questions, let us know, your Keysight team, and have fun with baseband link. Thanks.